Neural networks are general function approximators. That is, they map some input to some output, modeling an arbitrary underlying function. In case you've missed the previous video of the Neural Networks from Scratch video series on my channel, I would highly recommend you watching that video in advance to this video. There we covered the very fundamentals of neural networks and gave an intuition to the general approximation theorem. As we stated in the last video, neural networks have the capability to many any arbitrary function. But that in and of itself is not very useful, because most of the times in reality we don't know the underlying function in advance. But even if we would know the underlying function, then it wouldn't really make sense to try to model the underlying function inside such a network. That's kind of useless and useless manual labor. So in reality, we most of the times don't know the underlying function. But what we might have are examples of inputs and outputs. Inputs that map to an output. So for example, let's say we have a list of attributes for houses and the prices for those houses. So we have examples of attributes of houses that map to some price of that house, or we at least assume that they have some influence on that price. And what we now want to determine is how the individual attributes, that could be the size of the house, the location, whether it's near the sea or whatever, how these little attributes contribute to the price. We want to learn the underlying function from these examples we gave. And I will tell you in advance that this is an excellent use case for a neural network, and we will see why. So now one could ask, how is that possible? How can we infer a function just from using examples that have the input of that function and the corresponding output, without knowing the fundamental calculations within that function? In a neural network, that would be the individual weights and biases. How do we have to configure the individual weights and biases in order to model a function? How can we infer the weights and biases to model that function given by the example? And that is exactly where the backpropagation algorithm comes in. The backpropagation algorithm enables us to get the weights and biases of a neural network in an automatic way, such that we optimally model the function given by the examples. Let's start with an example where we know the underlying function. Okay, so let's take a look at the XOR function. The XOR function takes two inputs, that is x1 and x2 in this case, and produces the XOR of x1 and x2. And that is defined as, when we write all of this table out, so we have all of the possible configurations of x1 and x2, and obviously x1 or x1 XOR x2 is only one if and only if one of x1 and x2 is 1, so only in these cases. If we want to restate the XOR function as a compound of AND, NOT, and OR operations, we would come up with something like this. That is x1 and not x2, or not x1 and x2. So it's either x1 is true and x2 is false, or x1 is false and x2 is true. So this is XOR. But in this canonical form where we just use AND, OR, and NOT. And if we were now to translate this into a neural network, we would now need a neuron to model this here, this AND, a neuron to model this, and we need a neuron that combines these two and says, okay, either one of these is true or the other one. So we can infer from this canonical form that our neural network can look like something like this. We obviously have now again both inputs, x1, x2, and all of the layers are fully connected. For each neuron we obviously also have a bias, so we model that as well. Okay, so, and for this network, as we know the underlying function, we can manually infer the weights. One thing we were missing is the activation function. As we try to model a function that basically can output 0 or 1, the step function might be suitable. So the step function, if you recall, the step function is defined as 1 when x is greater than or equal to 0, or 0 if x is less than 0. And now we can fill out the weights. So this is a possible configuration, and let's try to plug values for x and x1 and x2 in there to see that this actually is the correct configuration. So if we plug in 0, 0, 0 for x1, 0 for x2, we get, as before, a neuron does a sum over the weights multiplied by the inputs plus the bias. In this case, that would be 1 times 1 for this neuron. 0 times 1, that is 0, plus 0 times negative 1, that is 0. And 1 times negative 1, which is negative 1 all the time, so minus 1, this gives minus 1. So the intermediate output is minus 1, and we see if we apply the step function, minus 1 is less than 0. So this neuron outputs a 0. This neuron now outputs a 0. For this neuron, it's kind of the same thing. 0 times negative 1, 0 times 1, minus 1 is also minus 1. So this neuron also outputs a 0. 0 times 1 plus 0 times 1 minus 1 is negative 1. So the output of this neural network is 0. And for 0, 0 as an input, we would expect the XOR function to output a 0. So that is correct. Let's do another configuration as well. 1 and 0. So let's plug in 1, 0. 1 times 1 plus negative 1 times 0. That is 1. Minus 1 is 0. X is greater than or equal to 0. So this outputs a 1. And for the second one, we have 1 times 0. That is x2. And negative 1 times 1. That is negative 1. Minus 1 is negative 2. So that's less than 0. This outputs a 0. We have 1 times 1 plus 1 times 0. That is 1. Minus 1 is 0. So x is greater than or equal to 0. This outputs a 1. The same thing for the inverse. Then this neuron here will output a 1, and this will a 0. Same, still a 1. And the fourth configuration, which is 1, 1. 1, 1. So this is 1, 1, minus 1, minus 1 is minus 1. So this will output a 0. We have 1 times minus 1 is minus 1, plus 1 is 0, minus 1 is minus 1. So this will output a 0, and this will output a 0 as well. What we can actually see is we implemented the XOR function with this simple neural network, where these neurons effectively add like OR and 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 NOT nodes. So where we have this negative 1, we apply a NOT, and using the bias and the weight configuration, we can model AND and OR. Okay, as you can see, if we know the underlying function, it is possible to model a neural network that maps that function. But why would we do that? That's a lot of manual effort for basically nothing. What we want to do is we somehow know that this network can come up with a solution. But now what we don't want to do is we don't want to specify all of these weights. So the last time we tried to come up with a configuration that satisfies the function. Now we want to infer the weights, and we want to infer the weights by providing examples. And we said our examples look like this. We have 0, 0 that maps to 0, 1, 0 that maps to 1, 0, 1 that maps to 1, and 1, 1 that maps to 0. So we hand the neural network these examples, and it should figure out the weights on its own. This is the basic idea of backpropagation. Give the neural network some data, infer the weights and biases. And this fundamental algorithm, the backpropagation algorithm, has not been changed since its inception in the 1980s. And as you will see, a lot of the ideas that are fundamental to learning from data and machine learning are quite old, and they haven't really changed for a long time. So let's actually look at the backpropagation algorithm. The backpropagation algorithm basically comes down to three ideas. First, we need a forward calculation, a complete pass through the network, using some initialized weights and biases. Secondly, the backpropagation algorithm introduces the idea of a loss function that describes how much the output of the forward pass deviates from the expected output we gave as an example. So that is, for example, our neural network at the moment with these weights and biases calculates for 0, 0 a 0.5, while it should produce a 0. So there is some deviation. And this deviation is described by the loss. And the last step, the most crucial step, is to use something that's called gradient descent to update the individual weights and biases with respect to the loss in order to minimize the loss. So the loss plays a crucial role in this whole picture. Let's first look at the loss. We said that the loss function has to represent some measure of badness of the output of our neural network in comparison to the expected output. For 0, 0, our neural network should output a 0. That would be the expected output, and that expected output we now denote as y hat. And we said, a forward pass through our network gives us 0.5. This is the y of the network. And the loss function now has to tell us how bad our prediction is. That is, the higher the loss, the worse the prediction, and the lower the loss, the better. So one could actually come up with some loss function that looks like this. That's the absolute difference between y and y hat. And the larger this absolute difference, the worse. What we could also do is say, okay, we take the difference between y and y hat. That is not sufficient because we don't know in which direction the difference points. So we take the square to make it positive. And for some unknown reason right now, we take half of this. So as you can see, you can really come up with any loss function as long as that loss function represents the measure of badness of the prediction, and the lower the loss, the better. So let's come to the core of backpropagation. That is the idea of gradient descent. So if we have any function, like for this case, x squared, and we want to find the minimum of that function, what we intuitively do is we calculate the gradient with respect to all of the parameters, that in this case is only x. And in this case, the gradient with respect to x is 2x. And when we would now draw arrows at each of the individual x's that represent the gradient at each individual point, they would point away from the minimum. So here maybe this is x is equal to 2, that would negative 2, that would be negative 4. 2 times negative 2 is 4. So that points in this direction, this, and so on. And on the other side, let's say 2 times 2, that's 4. So this points in this direction, in this direction, in this direction, this direction. And what we notice is that the positive gradient with respect to the parameters always points into the steepest ascent, where the function goes the most upwards. We can now use that information and turn the sign around. We can calculate negative d dx of f of x. So that is equal to negative 2x, and suddenly all the arrows point into the direction of the steepest descent, where the minimum of the function is. And in this case, we can actually calculate the minimum, but in reality, when we have complex functions, it's not that easy. So we can take that idea with a negative gradient pointing into the direction of the steepest descent, come up with a way to optimize all of the network's parameters in order to minimize the loss. The loss function is the function we try to optimize. So when we calculate the negative gradient of the loss function with respect to all of the network's parameters, we would know how we have to update our parameters in order to minimize the loss. And that's it. That's backpropagation. Calculate dl, where L is the loss function, with respect to all of the weights and all of the biases. Update the weights and biases. So the new weight is equal to the weight plus dl dw with some learning rate. And the new bias is equal to bias plus the learning rate times the gradient. And do that repeatedly. So ultimately, how you can think of backpropagation is the following. We have our network parameters that somehow have an influence on the loss. And at the moment, our parameters are here. The parameters are basically the weights and biases. And those parameters produce a loss at this level. Now we calculate the gradient, the negative gradient of the loss with respect to all of the parameters, and that we said will point into the direction of the steepest descent. So somewhat like this. This is dl d params. Now what we do is we update our params with this vector. So the next params will maybe be somewhere here. And we do it again. Get the next gradient. Update our params. And at some point we end up in some kind of optimum. And in this case you see, okay, this is not even the global optimum. So maybe we should have updated our weights a little bit different. But basically it boils down to this. So I hope you got from this video an intuition as of how backpropagation works and how neural networks are able to learn from data with some very, very basic principles. In the next video, we will look at our example again, our XOR example, and we will calculate the gradients with respect to all of the network's parameters. There are some tricks there and we will dive into those. So I hope you liked the video. If you want, you can like and subscribe. Wish you a nice day and see you. Bye.